Hi everyone, and welcome to Chapter 13. We're going to be talking about ANOVAs this time. Up to this point we have looked at t-tests. T-tests are when you compare two groups and you want to see if there's a difference in the means. We can do independent t-test where the groups have nothing to do with each other and we're just seeing if there's differences between those groups. Or we can use dependent or pairwise t-test, and that's where the same individual is tested more than once. And we want to compare to see if there's a difference in, say, performance or whatever it is that we're measuring. Now we're going to be looking at differences among more than two groups, and so you can follow the chart here. Differences, yes, we're going to be examining differences. No, the participants have not been tested more than once. How many groups are we dealing with? Two or more. So we're going to do a simple analysis of variance. As I mentioned, analysis of variance, also known as a simple analysis of variance or one-way analysis of variance, or also known as one-way ANOVA, is a test of the difference between the means of three or more groups, or IVs, independent variables. Okay, so here's some samples to tell you kind of so you can visualize what they would look like. So let's talk about study time in increments of 4 hours for the NCE. So if I had a group who studied 4 hours, a group that studied 8 hours, and a group that studied 12 hours, I could look at their NCE score to determine if there were differences in that, with the assumption being, of course, that the study time impacted the score. I can also look at first year, second year, and third year doc students and measure their research confidence. I can also look at students in a statistics class at week 0, week 4, and week 8 and do a knowledge test to see what they've learned. And again, we won't know what those differences are, we'll just know that there is a difference. This technique, as I mentioned, is the analysis of variance, because the variance due to differences in performance are separated into variance that's due to differences between the individuals, between the groups, and variance due to differences within each group. This will make a lot more sense as we start to do the math. The T statistic for ANOVA is an F test. Now, there's different types of ANOVAs. You have the simple analysis of variance, or one-way ANOVA, which we're going to be talking about in this video, and that's really used when there's one factor or one treatment variable that's been explored and it has more than two layers, okay, like these up here. We also have factorial design, which we'll talk about in a different video, and that's when we're exploring more than one treatment factor. So maybe we're looking at these things here, but we're also adding in gender, and maybe I'm looking at male and female, or I'm looking at cohort in a different group, and so you add an additional treatment factor there, and then you can do factorial design. 3 by 2 just means that you're going to have groups 1, 2, and 3, and then, like I said, male and female, and we'll be looking at these more when we talk about factorial design. Okay. Now, when you want to measure more than two things as a test or dependent variable, then you move into something called a ANOVA. And I'm going to go ahead and mention that here. We don't talk about that in this class, but many of you in your dissertation work or research work will be looking at ANOVAs, which are wonderful tools, but it just means that you have more than one dependent variable. So in that example of NCE score, maybe this school also offers the CPCE. And so I want to look at their CPCE score and their NCE score. So now I have two scores that I'm collecting, two dependent variables. And so that would mean I would do a ANOVA. So with a ANOVA, you have more than two groups and more than one independent variable. So when are we going to use an ANOVA? Well, we're going to use an ANOVA when there's a simple ANOVA, a one-way ANOVA actually. When there's a one dimension or treatment, there are more than two levels of a grouping factor, and we're looking at differences across the groups in those scores. Now here's the formula. It seems pretty simple, but it's pretty complicated actually to build, and we'll talk about that in a minute when we do our example. So it is the F score equals the variance between groups divided by the variance within groups. As the F value increases, it's more likely that our findings are due to something other than chance. I mean, ideally what our intervention is or whatever it is we're measuring, but we're always skeptical if that's the only thing we're measuring. But the larger your F score, the more likely it's due to something other than chance, okay? So let's do an example. Imagine we have 3 groups of preschoolers and their language scores. Group 1 spends 5 hours per week in preschool. Group 2 spends 10 hours per week in preschool. And Group 3 spends 20 hours per week in preschool. So we have our scores here. We're going to follow our famous 8 steps, just like we've done in other statistical tests. We're going to state our null and research hypothesis. Now, the null hypothesis, which states, and it's shown in your book in Formula 13.2, states that there's no difference among the means of the 3 different groups. ANOVA, also called the F test because it produces the F statistic or the F ratio, looks at the overall differences among groups. Okay, so here you can see this is what the formula looks like. I've recreated it here. It doesn't look at pairwise differences, so it's not looking at M to 2, group 1 to group 2, group 2 to group 3, group 1 to group 3. That's not what we're doing in ANOVA. We're just trying to see if there's a difference. So our null hypothesis is clearly going to say there's no difference between these 3 groups. So when we look at our research hypothesis, now remember this is looking at the population, right? Our null always looks at the population, whereas our alternative or research hypothesis always looks at the sample that we have. So here it states that the overall difference of means is not equal. This should actually be a not equal. So let me fix that very quickly. Where's our not equal? Right there. So that should be not equal. Okay. So we want to make sure that that's our alternative hypothesis, saying that this particular sample we're saying isn't equal. Okay. We're not saying where the differences are. We're just saying that there is a difference. We're going to set our level of risk. Again, this is the percentage that we're willing to accept that our findings might be due to something other than chance. So for this one, as usual, we're going to set it at 0.05. We have the discretion to set it, lower at 0.001 or whatever, but for now we're going to go 0.005, which means I'm willing to accept that 5 times out of 100. I could be wrong. And then I'm going to select the appropriate test statistic, which we did at the top. These preschoolers are only being measured once, and there's 3 groups. Because there's 3 groups and they're only being measured once, and I want to know if there's a difference between these groups, I need to use an ANOVA. I compute the F statistic value. So I've got to compute this F statistic value, right? And the way I do that is I've got to do a lot of math. And I really want you to do this math for this first problem. After that, we'll be able to use SPSS, but I want you to really understand how this works. So it's going to be really important to pause the video and calculate all the math and see if your math matches my math, and then we will do it through SPSS as well. So remember, we're trying to calculate this F ratio, and the ratio is the variability, the variance between the between groups and the within groups. So when I look between each group, how much difference is there, and within each group, how much difference is there. The between group sum of squares is equal to the sum of the difference between the mean of all scores and the mean of each group scores, and then squared. This will make more sense when you see the math, I promise. The within group sum of squares is equal to the sum of the difference between each individual in the group and the mean of each group, which is then squared. All right, and the total sum of squares is equal to the sum of the between groups and the within groups. All right, so to get us started, and I'm actually going to put this down on the next page so that we have it all on one page. Okay, so come on down. There we go. All right, so these are the scores that I gave you previously in the chart. All right, so what I want you to do is I want you to square each one of these scores. Okay, so square each one of these scores. And then here you're going to calculate the N of 1, group 1, right? And so the N of 1, you just count how many scores there are. And so this is going to be the N value for each one of these groups. Down here, you're going to do the sum of X, right? So how much is this, right? So this is going to be the sum of X right here. So you're going to put the sum of X right here. So what does this column equal? And then this one is going to be the sum of X squared. So when I do this, this column right here will represent this, okay? And so the same thing is true for group 2 and group 3. So fill in this chart as much as you can and then restart the video. So pause the video right now and see if you can sum up these scores, square each score, then sum up the total for the sum of squares. Okay, so hopefully you've gotten the same numbers that I have. So when you square 87, you get 7,569, 86, you get 7,396, etc. When I total up the total number of the total scores here, I get the sum of x is 766. When I count the groups, I get n is equal to 10. When I sum up the squares here, I get the sum of the squares are this number. And so you can see each column has been completed. So in this particular chart, which will help you fill out this formula, I've moved these down. So here's my sum of squares. Here are my this is my sum of squares, and this is my sum of scores. Now, I also have to calculate mean, and hopefully you remember how to do mean. So for mean, we're going to total up the total number of scores, and we're going to divide it by the sample, the n, right? So x, total number of x's divided by n, and that will give us our mean for each one of these, which I will uncover here. Okay, so those are our means. It's not surprising because, you know, it's only 10 people in the group, so I just need to move the decimal over one. Now, we need to also do the sum of x squared. So that's where I take this number and I square it. Okay, and for group 2, I'm going to take this number and I'm going to square it. And for group 3, I'm going to take this number and I'm going to square it. And when I do, I'm going to then divide by n, which is by 10, and that'll give me this score right here, which we're going to need in a few minutes. Okay, now you can see that these are little n's because these are each one of the samples, right? This big N means that it's the total number within the ANOVA of participants. So in this particular case, that's going to be 30, right? 10 plus 10 plus 10 equals 30. Now I have to do the sum of x. Now don't get freaked out by the fact there's two summations there. If you think about it, it makes sense. So here's the sum of x. I have sum of x here, sum of x here, and sum of x here. So if I add up each one of these numbers, I will then get the sum of the summation of x. Boom. Okay? Very similarly, here I need the sum of the summation, and then summation of x, and then I square it. Okay? So what I'm going to do here as I'm going to use these numbers, right? So I have the summation of x, because I've got it right here. So this piece right here, I already have. It's right here, the 2,534, right? So I'm going to move that number down here. Then I'm going to square it, and when I square it, I'm going to get this number, okay? Because I'm going to divide it by 30. That's what the n is, 30. So I just square this number, and then I divide it by this number, and I get this number. Okay, now this is the summation of the summation x squared. Now I've got the summation of x squared here, right? So it's just telling me to add up each one of these numbers. So I add up those numbers, and when I do, I get this number. All right, now this one is the summation of x squared. Okay, there's summation of x squared right here divided by n. So it's this whole formula right here. I already have that. I have them right here. Boom, boom, and boom. So now I'm just summing that. Okay, and there should be another parentheses there. Okay, so I'm going to add up these numbers, and when I do that, I'm going to get this score. Okay, and so from that, I then have the numbers that I need to calculate this formula. Okay? Okay, now we're almost there. So now that we have these calculations calculated, we now need to create what's called a source table so that we can calculate our F statistic. So first things first, if you remember from the formula, we need to know the between and the within. So how are we going to do that? So to find the between sum of scores, we have to take the sum of each group score divided by n, which is this one, and we have to divide that by the sum of all the scores across the group squared divided by n. So when you pull that information from over here, we end up with these numbers. This is your sum of each group scores divided by n, and this right here is the sum of all the scores across groups squared and divided by n. So just match your formulas up and you end up with this number. Now for your within sum of scores, you're going to have the sum of all the sums squared, and you're going to divide that by the sum of each group score divided by n. So again, pull that information, matching your formulas, bring those down, and you'll end up with this score. For your total sum of scores, you're going to end up with the sum of all sums of scores here, and you're going to divide that by the sum of each group scores squared divided by n, and that gives you this number. All right, now I know this is a lot of calculations, but this is hopefully giving you some great appreciation for why we use SPSS. Now we're going to move to our source table. So this is what's called a source table and is what you're always trying to get when you're doing an ANOVA. So for our source table, we need to compute the sum of squares, or compute the mean sum of squares, which is simply an average of the sum of squares. These are the variance estimates that we're going to need in order to calculate our F score. Okay. The first thing we have to do though is calculate these degrees of freedom. So how did I get these numbers? Remember, the degrees of freedom is that approximation of the sample or group size. For an ANOVA, we need two sets of degrees of freedom. We need the between groups degree of freedom and the within groups degree of freedom. The between group estimate is K. All right, so this is going to be K minus, oops, I want a small k, minus 1 equals. Okay, I'm going to make this a little bit bigger so we can see that as a formula and not have it all scrunched up. There we go. All right, so K minus 1. All right, now what is K? K is the number of occurrences, right? So in this case, we have 3 groups, right? So we have 3 groups, so that's how many times we're measuring our occurrences of measure. So K equals the number of groups in this situation, so that would be 3 minus 1 equals 2. All right, so your K is 3 in this situation. Now, for your within groups, you need N minus that K. K. All right, and so in this case, that's going to be 30, remember, because we had a total number of sample, minus K, which is our 3, and that's going to equal 27. So in this situation, that is our 27. Now, our total sum of scores is 29 because it's this degree of freedom plus this degree of freedom. So in this case, it would be 2 plus 27 equals 29. All right, so I'm going to move this source table down so that we have it on one page and we can see it really clearly. So we're going to scroll down. There we go. All right, so in this case, we have calculated the degrees of freedom, which we're going to need here in a second. So our degree of freedom are these numbers that I've bolded. Okay, and the F ratio is simply a ratio of the mean sum of squares due to the between group differences to the mean sum of squares due to the within differences. So if we're using this formula right here, we're going to put that right here, then this formula is simply going to be F equals 566.54 divided by 64.39 equals 8.799, which we're actually going to say is equal to 8.80, I think. Yes, 80. Okay, but that's very tiny, so let's fix that. Okay, so this gives you your F score. And just in case anybody's forgotten how to get a mean, I want to make sure you understand where I got these numbers from, because I realized I just skipped that step. So what you're simply doing is taking the sum of scores, remember, the sum of x, and we're dividing it by the degrees of freedom, which in this case is representing our sample, right? So when I divide this number by 2, I get this number. Same thing with within sums. When I divide the sum of scores, which is just like our sum of x, by our sample size, which we're saying is 27, then I get this number. So it's just like mean. It's the same idea. It's just different names for different things. So these are very much like a mean, right? An x divided by n. So I'm taking the total of x and I'm dividing it by n. And I'm getting this. And then I'm setting up a ratio of this to this. And when I divide that, I get this number, right? And that means that our F score is equal to 88.799. I'm going to simplify that and just say F is equal to 8.80. You're certainly welcome to take it out to 4, but most F scores are reported with 2 decimals, okay? Now we need to determine our critical value, right? This is our obtained value. This is what, with the sample that we have, this is the F score that we obtained. Now we need to know the critical value. And just like we've done in the past, we're going to go to that appendix. We're going to go back to the appendix in Appendix B of our textbook. This time we're going to be using the F statistic book or chapter or appendix. I'm getting tired, okay. So here we go. We're going to go to the Appendix B and we're going to scroll down. That's for Z's, these are for T's. Now I need to find, here's the one for F, okay. So here's the critical values for analysis of variance, or F score. It's telling me what to do. Now in this case, I know that I have a couple of F scores, right? So how am I going to use this so that I can use this chart? All right, so let's go back to our our first task is to determine the degrees of freedom for the numerator. Okay, we already know what that is. Actually, we've actually calculated it here, and we've calculated our denominator here. So this is, remember, this is our numerator, this is our denominator, so we've already calculated that. So the degrees of freedom, the way that we actually write that in an ANOVA is we put the numerator first and the denominator second. So this is my between degrees of freedom and this is my within degrees of freedom, okay? And so I'm going to go ahead and cover this. The obtained score we know is 8.80, right? The critical value at 0.05 with 2 degrees of freedom and 27 degrees of freedom is this number. How did I come up with that? I go back to my chart here. All right, and so the DF for the denominator, and I'm thinking, okay, that's 27, so I'm going to go down here. Let's look at the top of this first. The type of error, so I'm going to look for 0.05, and then I'm going to look for the degrees of freedom in the numerator. My numerator is a 2, right? So I'm going to stay in this 1, 2, 3, 4th column over, right? The 4th column over, so I want to find 27 on this column, 0.05 on this column, and then I want to go to 2 columns over from that to find my answer. So I'm going to scroll down till I find 27. Here's 27. I want to go to 0.05, right? Because that's the p-value I selected. I'm going to go over to this column because this was 2 for the numerator, 3.36. Okay, so again, this is your denominator or your within degrees of freedom. This is your p-value. And then this column represents the 2 from the between group degrees of freedom that I calculated. Okay, hopefully that makes sense to everybody. All right, and so the obtained value, which I got up here, is the 8.80. My critical value is 3.36. Okay, so 3.36. So now I need to compare this with this. And the obtained value, as I said before, the one that we calculated is 8.80. The critical value is, the critical value for rejection at the 0.05 level for the 3 groups is 3.36. So I can see this number is much more extreme than this, and it says if the obtained value is more extreme than the critical value, the null hypothesis cannot be accepted, right? So we are going to, the null hypothesis is rejected. If the obtained value does not exceed the critical value, then the null hypothesis is the most attractive explanation we have. In this case, it's definitely more extreme. So where we have a significant enough difference to say that there is a difference among these groups that's more than just chance, right? Now, what does this mean? And this is where it's really important. So our decision is that the probability is less than 5% on any test of the null hypothesis that the average score of each group's language skills differs due to chance alone, rather than because of the treatment, which in this case is the number of hours in preschool. Because we defined 0.05 as our criterion for the research, it's more attractive that the null hypothesis that our conclusion represents a significant difference among the three sets of scores. But what does this all mean, okay? And this is where it's really important to understand. I don't know where that difference is. I just know that somewhere among those scores there is a difference. So when I note that, I'm just going to say my interpretation is the three groups of preschoolers demonstrated differences in language scores. That's it. That's all I can really say. Now, why don't we just run multiple t-tests, right? That seems like so much easier than what we just did. So to run a t-test, we'd have to run comparison of group 1 to group 2, group 1 to group 3, and group 2 to group 3. And if we set our p-value at 0.05, then that means that we're willing to accept that 5% chance that we're wrong, right? Well, here's the problem. Each time you run a t-test, that combination is increasing exponentially even the type of error that you're getting because you're using the same data. And every time you run on the data, you're increasing your chances that something else is at play. All right, so when we calculate the type 1 error, this is the formula we use. And that is 1 minus the alpha to k, k being the number of occurrences, right? So the alpha is our type 1 error or p-value, okay? And so that's important to know. And then k is the number of comparisons that we've run, right? So here we've got 1 comparison, 2 comparisons, and 3 comparisons, right? So that's going to make our k a 3. So let's look and see what happens. So here's our formula again. All right, and I'm going to plug in that information. So 0.05 is my p-value. I have 3 comparisons. When I do the math, this is what I'm going to get, 0.95 to the third. When I cube that, I'm going to get this number. And then what this is going to say is that if I were to run 3 t-tests on the same data, that at the 0.05 p-value, I'm actually giving myself 14.26% chance that chance explained what I did and not what I'm actually testing. And I don't want to have that much chance. I don't want to have that much error in my study. So when you run multiple t-tests, you're actually exponentially increasing each time because of the cube, right? So if I run it 3 times, then I'm cubing it. If I run it to 5 comparisons, then I'm going to raise it to the 5th power. And so each time I run the same test or on the same data, I'm increasing my error. So that's why we want to use an ANOVA instead of a t-test repeated. Now we've talked about effect size many times, and I just want to go over this, that effect size for an ANOVA is actually called an eta squared, and this is what that looks like, and that's the between group sum of squares divided by the total sum of squares. Remember, we have that up here in this chart right here. Okay? And so what I'm going to do is pull from that chart, and I'm going to use those numbers, and I'm going to determine what the eta is for our sample. So when I calculate the eta for the test that we just ran, I get an eta squared of 0.39. Now I'm going to use this chart right here to determine what that means. And if I look, okay, if it's 0.01 to 0.05, then it's going to be small. If it's 0.06 to 0.013, then it's going to be a medium. If it's 0.14 or higher, it's going to be large. So this is saying this is a large effect size. This is something that we need to pay attention to. So in this particular case, we're going to say according to the small medium guidelines for eta squared, 0.39 is a large effect. So that means that there's something here. We should be curious about this. Now let's go into SPSS and run the same information. All right, so I'm going to pull up my SPSS over here. Here's the data. So this is chapter 13, data set 1. So you can pull that from the data set. And you want to get that pulled up. So if you need to pause the video so you can get the data set pulled up. the same data we were just using. All right. Once you get your data pulled up, then we're going to run the SPSS for that. So once we've got the data entered, right, what we're going to do is click Analyze, and then we're going to do Compare Means, because remember that's what we're doing, and we're going to do a one-way ANOVA right here, and then we'll get the one-way ANOVA dialog. And we're going to click on the variable named Group, okay, because that's the first one that we want to move it to. We want to move it to the factor box because the group is our factor in ANOVA, right? Our dependent, right, the thing that we're testing is the language score. So we're going to put that one in the language score. And then we're going to click on Options, and we're going to do Descriptive because we want the mean, median, and mode. And we'll hit Continue. Now, I'm going to explain this later, but I also want to run post hoc, and I'm going to run this one, okay? There's lots of different ones. We'll talk about these in a little bit, but I'm going to go ahead and click this, okay? And I'll explain what it means later. And then I'm going to hit OK, and it's going to open up this, whoops, where'd it go? There it is. It's going to open up this chart. Okay, now this should look familiar to you because we actually calculated a lot of this and when we did it by hand. So here you can see it's got the 3 groups, the 5-hour group, the 10-hour group, the 2-hour group in 30. Here's our mean, standard deviation. Then here we have our scores, right? This is our source table, right? The source table looks very similar to what we just did, but wow, did they do it much faster than we did. Now, we know that we selected a 0.05, right? But what this is saying here is that this is actually significant at the 0.001 level. You know, so when we're computing by hand, we're guessing at the level that we should select. Should we select 0.05, 0.01, 0.001? But when you use SPSS, it actually tells you at what level it is significant. So this is really cool. I didn't have to guess. I mean, I set my null at 0.05, but this is saying, wow, it's even way better than 0.05. We actually can say that there's less than a 0.01 chance that we were wrong, right? And that it was by chance alone. So you can see very similar. We've got descriptive values, we have sum of squares for our between, our within, and our total, and then we have our obtained value, and we have the level at which that's significant. So all of that's really quite helpful and so quick. Oh, how fast was that? It was amazing. Now, one of the things that I've mentioned a couple of times in this presentation is that this score right here, this F score, only tells us that there is a difference. I don't know where that difference is. I don't know what that difference means. So here, is it that they're 5 hours it does better than the 10 hours, that is better than the 20 hours? I don't know. All I know is that there is a difference in this. So the reason I went ahead and clicked post hoc is because when you run an ANOVA, if you want to know what the difference is, you have to run the post hoc test as well. And in this one, I ran this particular type of post hoc test, and there's lots of different ones, but I ran this post hoc, and now what this is doing is it's actually running the comparisons. So what it's doing is it's comparing the 5-hour to the 10-hour and the 20-hour, the 10-hour to the 5 and the 20-hour, the 20-hour to the 5 and the 10-hour. So you can see it's running all the possibilities here, right? And so what it's doing is it's showing you where that significance difference is. And interestingly, it's between the 5 and the 20-hour, but not between the 5 and the 10-hour. You see these significance levels? So this one is not significant at the 0.05. This one is significant at the 0.001. So what that tells me is, oh, okay, there's not much difference between going from 5 hours to 10 hours of preschool, but there's a huge difference going between 5 hours to 20 hours of preschool, right? There's no difference here between the 10, between either one of these. This one is just a repeat of this one, right? It's just the other way around. So these should be exactly the same when you look at these. Very important. And they're only the negative here because it's 5 to 10, and here it's 10 to 5. Now, let's look at the 20-hour. Okay, again, significant at the 0.001, which makes perfect sense because it was significant here, right? And then the 20 to 10, not significant, which is not surprising because that same one was ran here, Okay, so these are repeating in some ways, right? But what I notice is that 5 to 20 is really the only one that has a very strong significant difference. Okay, so this post hoc is an essential part of your ANOVA. It's not part of the ANOVA in the sense of the calculations, but it's a second test that's running to then determine, okay, if there is a significant difference in the ANOVA, where is that difference? And how significant is that difference? And that's why you would run a post hoc. I hope this has been helpful in explaining ANOVAs, and I look forward to seeing you in class and talking about this more.